All right, we should be able to bring closure here to the 8.3 notes today. The last video, we had just talked about how you could actually perform the confidence interval for these means on the calculator, but it's very important that you're writing down all of your inputs and that you're writing down what the degrees of freedom are. Okay, so it tends to be confusing for people sometimes to distinguish between when they're supposed to use a z-score in their confidence interval and when they're supposed to use a t-score. And so here's a little acronym that I'm hoping will make this helpful for you. If you are doing confidence intervals involving proportions, which by the way are typically your categorical data, that is when you use z-scores, okay? So that is when you would use inverse norm to get your z-score. Okay, when you are doing confidence intervals regarding means, which is always your quantitative and numerical data, that is when you're going to use t-scores inverse t. And here's the acronym. The acronym is called ZAP-TAX, okay? I think the A in there is just so that there's a vowel and these make words that you can pronounce. But the Z is z-score and the P is proportion. The T is t-score and the X on tax with a bar over it stands for means, sample means, okay? So ZAP, z-scores with proportion, tax, t-scores with means. Okay, this just mentions here what's a typical thing that people do when they lose credit for maybe citing, you know, the normal condition on an AP exam. People forget to say that it was the central limit theorem, and specifically saying because the sample size was more than 30. Also, when the sample size is less than 30, a big mistake that people do not do, and they should, is they do not actually draw the graph of the data, which we're going to look at here in this next example, whether that's a histogram or a normal probability plot. You have to actually graph the data on your paper. You can't just look at it on your calculator and then say, because it has no extreme skewness or outliers, we assume normality, okay? You want to definitely say that, but you have to also draw the graph on the paper, okay? What should you do if you think that the normal condition isn't met? Well, if you think that it's not met, what you're going to do is you're just going to say, I don't think that this is meeting the criteria, but I'm going to go ahead and just proceed with caution. Okay, you never want to stop in the middle of the problem. You always want to continue on with the problem and just mention you think this condition isn't met, and so you're proceeding with caution. Okay, so here's an example of a problem where they're actually giving you the body of data. It says as part of their final project in AP Stats, Christina and Rachel, ooh, this is nice, that they randomly, so I'm going to highlight that because that's one of our conditions, they randomly selected, I'm going to go ahead and highlight the number in the sample, 18 rolls of generic brand of toilet paper, and they want to measure how well this brand can absorb water. So to do this, they poured 1/4 of a cup of water onto a hard surface, and they counted how many squares of toilet paper it took to completely absorb the water. And here's what their results were from these 18 rolls of generic brand of toilet paper. You know, in one instance when they did this, looked like it took 29 different squares. Here in another time when they did this, it took 20 squares for it to completely absorb the water. And so here we have 18 different samples, 18 different rolls. It says, construct and interpret a 99% confidence interval for mu, the true mean number of squares of generic toilet paper needed to absorb the 1/4 a cup of water. Okay, so we're going to start this the way we always have been here. I'm going to kind of move through these quickly because we've done several of these at this point. The state step, we're going to state what it is we're estimating. We are estimating mu, which is the true population true population mean number of squares of generic toilet paper needed to absorb 1/4 a cup of water. Okay, if you remember, there is one other element that needs to be included in this state step, and that is the confidence level. I'm going to say I'm going to do this at a 99% confidence level. Okay, now I'm going to move on to the plan step. This is the step where I first state the name of the inference procedure. This is a one sample t interval for proportions And then I'm going to go ahead and I'm going to run through my list of conditions. Okay, the first list is random. I'm going to go ahead and say 18 rolls were randomly selected. Okay, 18 rolls were randomly selected. Okay, 10% condition. I think it's safe to say that there is definitely more than 180 of all generic rolls of toilet paper. Okay, now for the normal condition, it did not mention that the population distribution was normal. That's the easiest way that I could just cite that and be done with it. Also, I'm looking at my sample size, it's 18. That is not greater than or equal to 30, so I cannot use the central limit theorem. So my other option, if I'm given the body of data, which I am, is to construct some type of a graph for this sample distribution here, and then examine the graph for any extreme skewness or outliers. If I don't see extreme skewness or outliers, then I can mention that and then say, I'm going to go ahead and just assume that the population from which this was drawn was normal, okay? So this is going to be the number of squares. Okay, always label your graphs. And, there's not one specific thing that you could totally make a box plot. That would be fine. I just want to review with you how to make a normal probability plot. What you would do, irregardless of which graph you're making, you would need to go through and put all of this data, all 18 of those numbers, into L1. Okay, what you would then proceed to do is you would go into second stat plot, okay, and choose plot number 1, okay, and turn it on. And the normal probability plot, if you were going to choose a normal probability plot, is the very last graph, okay? It kind of, it almost looks like this pictured on that stat plot menu. Okay, normal probability plot. Make sure that your data is L1 there, and then you're just going to press zoom 9. Okay, and it will show you the normal probability plot. Now, you don't have to get super detailed with this, although it is important that you have your x-axis labeled, but you're just going to go ahead and just kind of eyeball, and you're just going to try to plot those points roughly. You can see that's what I did right there. Okay, I'm just looking, does this general trend feel like it's linear? Okay, and for the most part, it's pretty linear. Okay, there's no like major hook like that that's kind of occurring. So I'm feeling decent about saying that, and here's going to be my conclusion here. I'm going to say, since the sample distribution shows no extreme skewness or outliers, the sampling distribution is approximately normal. Okay, and that completes that. So now I'm going to go on to the do step here. Okay, and in the do step, I could do this one of two ways. I'll tell you, since you have the data already in your list, we could just do this on the calculator. I'm going to go ahead and write down just with the numbers plugged into the formula. I will tell you where I'm getting these numbers from is, because you'll notice, well, this should be an 18 here, we don't have the mean, and so you would need to calculate the average of all of those numbers by doing one variable stat on your calculator, since they're all in L1, and that would give you the sample mean, and it would give you the sample standard deviation from which you could then plug those into where you see I have these plugged into the formula. Okay, and then we would go on and we would do inverse T. Okay, this is a 99% confidence interval. So we'd want to split the 1% between the two tails for the area, and the degrees of freedom should be labeled as 17. Okay, if we did that, I believe that reveals a t-score of 2.90. Your other option, and this definitely would be the easier of the two options, is to press stat, go over to tests, go down and select T interval and select the input as being the data instead of the stats, because you have all these 18 data values already into L1. And then all you're doing is making sure that you're identifying L1 as your list and that it's a 99% confidence interval. You do have to write down, though, the degrees of freedom. That has to be written down on your paper. You know, if you're doing it with the formula, we're writing it right there. If you're going to use the calculator, must write that down. Okay, your interval then is 22.99 to 26.89, and our conclude step is we are 99% confident that the interval of 22.99 to 26.89 captures the true population mean number of squares of generic toilet paper needed to absorb 1/4 a cup of water. Okay, that brings that example to a close. And just to wrap up the rest of this notes page here, if you remember, we did this with proportions. At the end of those notes pages, we were trying to figure out what if when researchers are designing a study or they're wanting to, they haven't gathered their data yet, but they want to make sure that their results are within a certain margin of error of the truth. And so they want to know what their sample size should be in order to stay within a desired margin of error. Okay. Now, here's the trick with this is, you know, we've been talking about how we should use the sample standard deviation up here because we often don't have the population standard deviation. Well, if you're trying to figure out at the beginning of your research how many people you should survey, you won't have your sample standard deviation yet. Okay, you only get that after you've surveyed the number of people you've surveyed. Okay, and so for this reason, we're going to be using this, and let me explain this here. Okay, and so first and foremost, you'll notice I have the population standard deviation symbol back there. Okay, and because I have that there, that is why I'm using a z-score in front. Okay, here's the idea. The reason that the z-critical value is used instead of the t-value is because your t-score depends on your sample size. Okay, remember when we used table B? You use table B, and what row you use is dictated by the degrees of freedom. Well, the degrees of freedom are dictated by your sample size. Well, I can't use a t-score here if I have to use my sample size to determine that when at the beginning I'm trying to figure out what my sample size is. Okay, so we're going to use an estimate for your standard deviation by either using some pilot study or maybe looking back at historical data to try to estimate like what standard deviation should be plugged in here. Okay, let's look at an example so we can kind of see how this all is going to work out here. It says researchers would like to estimate the mean cholesterol level of a particular variety of monkey that is often used in laboratory experiments. And they would like their estimate, here it is, to be within 1 milligram per deciliter of the true value of mu at a 95% confidence level. Now, it says a previous study involving the same variety of monkeys suggested that the standard deviation of the cholesterol level is about 5 milligrams per deciliter. Okay, now keep in mind here, this formula up above is the formula for the margin of error. Okay, it mentioned that they would like their estimate to be within 1 milligram per deciliter. So I'm wanting the margin of error, that's the part that comes after like the plus or minus, to be less than or equal to 1. So we're within 1 milligram per deciliter. Okay, so my z-score that would be associated with a 95% confidence interval, and now I'm doing z-scores here, so that is inverse norm. Okay, that's 1.96. Okay, Then over here, if I look at my formula up above, they gave me in the problem 5 is what we're using from a previous study that they had used for their standard deviation. And it's really the n, the sample size, that we're really looking to solve for here. Okay, so we're going to go ahead and I'm going to multiply both sides by the square root of n that's down here, just to kind of pull that up to the other side here. Okay. And then to solve for n, I'm going to square both sides. And you do want to be a little bit careful with the way this symbol is facing. You know, this is a greater than symbol because it's pointing towards the n. You want to always round it up. And so we're saying that the number of monkeys that they should survey if they want to be within 1 milligram per deciliter is 97, or more monkeys would be fine. Okay, let's try one more of these here. It says a counselor wants to estimate the average number of text messages sent by students at his school during school hours. He wants to estimate this at a 99% confidence level with a margin of error. Here it says at the very most 2 texts. Okay, so I'm wanting my margin of error to be less than or equal to 2 text messages. A similar study at a nearby school discovered that the number of texts sent during school hours had a standard deviation of about 5 texts. Okay, so I'm going to be using a 5 from my previous study from a similar school nearby, 5 for my standard deviation. This is a 99% confidence interval. Remember, these are z-scores now. Okay, so this is what I would plug in here to get my z-score of 2.58. Okay, I'm going to go ahead and do the same thing we did before. This is just the algebra part to this. You guys should be comfortable with this. I'm going to multiply both sides by the square root of n. Okay, whoops. I'm going to divide both sides by 2, and then we are going to square both sides here. I'm going to move the n over to this side here. Initially, I get n greater than or equal to 41.6025. I should round that up and say that they should at least be surveying 42 students or more if they want their confidence interval to be within, at the very most, two texts for their margin of error. Okay.